Okay, welcome everybody to our final session of the afternoon and the day. And so our speaker is Adam Bateson, who will speak about fragmentation and melting of the seasonal sea ice cover.
Okay, hello everyone. Yeah, so I'm Adam, and yeah, there's kind of several co-authors on this work. So obviously Danny Felton, David Schroeder, Yan Wang and Phil Huang, who we just heard from before the break, Jeffrey Lee from the Met Office, Evgeny Aksonov from National Insurance Centre in Southampton, and Lucia Hoskova, who was at University of Reading during the time of this work, but she's now at the University of Hawaii, Manoa. Okay, so yeah, so this title, Fragmentation and Melting of the Seasonal Sea Ice Cover, this was the title of my PhD, which I finished completely last year. And a lot of this work was kind of looking at modelling the sea ice floe size distribution and its impact on the sea ice cover. So in my talk today, I'm kind of going to go through some of the key results from my thesis, and then highlight kind of how we're going to move forward with some of those results moving forward. Okay, so we've heard a lot already about the sea ice floe size distribution today. We'll just kind of summarize. So the floe size distribution, or FSD, is a term we use to kind of describe the size of floes in an ensemble. So we can kind of see like some observations of the FSD on the left there. And yeah, we see this quite huge range in scales from just meters to tens of kilometers. Flow size can be influenced by both mechanical and thermodynamic processes. So we've heard already today about kind of wave breakup of flows, and also Phil showed some examples, well, also lateral melting, and Phil also showed some examples earlier of how kind of melt ponds might drive the breaking apart of flows as well. But actually being able to kind of model the flow size distribution and its impact on the sea ice cover, it is challenging because of the range of scales involved and the range of processes involved. Okay, so in this talk, we're going to, I will kind of describe two alternative approaches to modeling the FSD, a power law approach and a prognostic approach. And kind of the overall aim is to kind of understand the potential kind of range of FSD impacts on sea ice evolution, and and to a certain extent the state of FSD modeling as well. So in part one, I'm going to use this power law approach to understand the sensitivity of the simulated sea ice mass balance to inclusion of an FSD model within kind of the range of FSD states that the observations show. And in part two, we'll compare the impacts of the two different approaches to modeling the FSD, both in the present day and within a future Arctic. And then time dependent, in part three, we'll kind of explore the limitations of kind of a new brittle fracture scheme that kind of Bill alluded to earlier, and that we've introduced to the prognostic model, and how the physical fidelity of the scheme could be improved. Okay, so just to summarize kind of the model setup before I go into the sections. So we're using all our simulations are in standalone size, but we have a prognostic mixed layer model, so we can capture some motion feedbacks by the mixed layer. And we also include the form drag scheme of Samados et al. 2014. So our reference run uses a fixed flow size of 300 meters. In part one, we just consider a simulation of simulations of the power law model. We have several simulations of variable parameters. In parts 2 to 3, we consider a power law setup with a fixed set of parameters where the extent has been determined from observations. And we also consider the oh, I think we've got some. Yeah, just going. And yeah, we also think about the prognostic flow size thickness distribution, which we heard about earlier, I think, from both Betty and Chris, and we've also introduced this new representation of brittle fracture. So FSD, yes. So in our setup, the FSD models can impact the sea ice evolution in both parts 1 and 2 and 3 via the lateral melt volume. So in terms of lateral melt, the lateral melt rate is proportional to flow perimeter, and also via the form drag scheme. So in the form drag scheme of Samados et al., there is a flow edge contribution to form drag. So we've modified that scheme slightly to account for the FSD. And our spin-ups are slightly different. So for parts 1, it's 1990 to 2006, and then we do an analysis in 2007, 10 years, 2007 to 2016. Part 2, spin-up is a bit longer, 1980 to 1999, and our analysis from 2000 to 2016. Okay, so going to part 1. So we have this Whipple FSD or power law model. So we have, within this model, we have several kind of key defining parameters. We have a dmin, which is the lower flow size cutoff, dmax, which is the upper flow size cutoff, and we also define this variable low size parameter L-var, and this evolves in response to several different processes. So lateral melting, wave breakup of flows. We use our wave model that we use is based on Williams et al. 2013 paper. The two papers, those who are aware of that. And then it also responds to freeze. We have a restoring in winter during conditions to freeze up, and also advection. And between the min and L-var, the FSD follows a power law with a fixed exponent. So we have alpha, which kind of defines our exponent. Yeah. And to determine the parameters for this sensitivity study, we kind of looked at the range that we see in observations. So in particular, we kind of looked at Stern et al. In 2018 kind of considered the range that summarized several different series of the observations of the FSD, capture the range. And kind of from this, we got a range of exponents from about -2 to -3.5. The majority of simulations kind of within. To be clear, this is the number distribution, not the cumulative distribution. And then for dmin, it's quite difficult often with observation of flow size to determine when, because often you see kind of tailing off kind of power law type behavior, but it's difficult to assess whether this is a physical behavior or due to like image resolution. And similarly with dmax, kind of there's limitations. So for both, we've gone for a range of 1 to 50 meters for dmin and a kilometre to 50 kilometers for dmax. Also, we defined this work a new kind of way of characterizing FSD called the effective flow size. And the idea of this is kind of a single flow size, which gives us kind of the same total, perimeter density as a flow size distribution. The idea being that so a set of single flows will give the equivalent melt rate for this size, will give the equivalent melt rate to kind of an ensemble of flows of various sizes. And given that both of our impacts of the FSD are proportional to the perimeter, so the form drag and the melt rate, this is a useful way of kind of being able to characterize and understand the impacts of including these processes, these models in size. This is just an example of some output. So we can see here, like we've defined it from the given standard size without an FSD model considers flows to be 300 meters. We can kind of see the transition from flows larger than that in the model, so across much of the pack ice, to small flows smaller than 300 meters, so towards the outer MAZ in this case. So here we don't really expect like enhanced lateral melting within and towards the outer MAZ. Okay, so we ran a set of simulations to explore model sensitivity to these parameters. So we did 16 simulations where we paired each exponent within the range 2 to 3.5 with 4 different values for dmin between the range of 1 to 50 meters. And we also ran a few simulations where we used standard parameters for the exponent and dmin, but very dmax. And actually what we found is there's quite a large sensitivity depending on the choice of these parameters. And obviously, as mentioned before, we kind of tried to select values that could be within the observed range. So we go from some simulations where we actually see small increases in September CX extent on the left and September volume on the right, so averaged over the simulation. So in some cases, we see small increases of like order of 1% or so, whereas in some simulations, we see reductions of over 20% in September CX extent and over 50% in September CX volume. Obviously, this particular case is an exponent of -3.5 and a dmin of 1 meter, so this would be a distribution very dominated by smaller flows, so you can perhaps contextualize it as an FSD dominated by, for example, pancake flows. But nevertheless, kind of we do see distributions of this sort in observations. So this sensitivity is substantial. Perhaps also of note is actually the mean effective flow size. We almost see a 1-to-1 correspondence between the kind of the change in extent and volume and this effective flow size, which kind of highlights its value in terms of being able to characterize FSD impacts. Okay, and finally for this section, we also did some sensitivities to different parameters. I just wanted to pick up on the kind of the wave attenuation rate. I mean, we've heard today already that kind of wave modeling it's quite challenging, and we use quite a simplified representation of kind of wave advection within the sea ice cover attenuation in this model. So we changed the attenuation rate by a factor of 10, which is reasonable given the assumptions made within the model. And actually, again, we see quite a substantial kind of change. So the difference in effective flow size is actually quite large from the MAZ, orders of 100 meters or higher. And this can lead to kind of substantial changes in the fractionalized area, especially towards the outer MAZ. Yeah, so changes of like 5 to 10% in CS concentration. And this has implications, for example, when you're trying to model the MAZ extent. Okay, so moving on to part 2, so FSD model comparison. So obviously this power law model is kind of useful as a simplified representation of the FSD state and allows us to kind of explore these different parameters. But also we do make substantial approximations. And obviously the question whether we can fully capture FSD impacts within the constraints of those approximations. So to kind of explore this, we've had a look, we did some work using the prognostic flow size thickness distribution that we heard previously from Letty Roach. So kind of our base version was the 2018 Roach et al. Version, but we also include the wave-dependent flow formation scheme that we see in the 2019 paper, and we also include this new brittle fracture scheme. So this is just an example of output from the model, and the appeal of this approach is you don't have to make assumptions about the shape of the distribution. Instead, it emerges at process level. Like firstly, that means you can kind of understand how the FSD might evolve, and secondly, there are potential like feedbacks and impacts that you can kind of capture using this sort of approach as opposed to a fixed shape. Okay, so we introduced this brittle fracture scheme, this idea was motivated by so Phil mentioned earlier the Garardi and Lagomarsino paper, and this paper kind of showed, as Phil mentioned earlier, that certain like observations of the FSD could be fitted by a parallel with a specific exponent, and they speculated that actually idealized models of brittle fracture, so like this not necessarily sea ice but just idealized brittle materials when undergoing brittle fracture events form the fragment size distribution is a power law with an exponent of -2. So kind of on this, we wanted to kind of capture the effect of these sorts of processes so there's two kind of processes. Firstly, in-plane brittle fracture events that happen kind of within the winter pack ice, especially within sea ice. But also these kind of winter features that form in sea ice. So we've heard a bit about the kind of linear kinematic features as well. And like leads, often these kind of freeze up or heal, but then there continue to be existing weaknesses along these lines in the sea ice that persist going into the melting season. And actually, melt ponds can form along the existing weaknesses, or they're already thinner. And then with these melt ponds forming, they become thinner and thinner, and locations of enhanced melting. And then they can potentially be lines of where the melt flows do sort of break apart in summer, for example, via the melt pond mechanism that Bill kind of highlighted earlier. That obviously will have an influence on the FSD shape. So if these winter fracture events are kind of determining the kind of fragment distribution that can then freeze and break apart again, then there's another mechanism by which these sorts of processes can influence the sea ice cover. So this scheme is an attempt to kind of capture these. It's quite a simple approach to doing this. So firstly, we only allow sea ice area to be transferred from large categories to adjacent smaller categories under the scheme, because obviously it's representing breakup and fracture of sea ice. So we only apply this where the number density gradient exceeds the exponent limit of -2. Yeah, so this is effectively kind of restoring towards this shape if the system was acting purely under brittle fracture. We only apply it to adjacent categories. And the sea ice area that we distribute is proportional, it's CATI. The ATI is the total sea ice area fraction in the large category, and T is a restoring constant. So this is kind of effectively a tuning parameter within the existing model. Okay, so earlier we saw kind of an extensive comparison of FSD model output to observations, but for this case we did a more simplified kind of comparison using some of the data from Bill and Yanan that was presented earlier. And in particular, we used some lower resolution data, and we focused on the range between 100 to 2 kilometers for this comparison. And this is just because this is a range we're confident that the epicenter is being well characterized in the observations. So in these plots, in pink and purple, we see the observations across these two sites. We also looked at the observations across a further site in the Greenland Sea and across additional time periods for each of the 3 sites. I'm just showing to you here as examples. So across all these sites, we found the kind of an average power excellent for the power law fit across all the sites. And actually we found that this, as an approximation, it did okay over this flow size range. So this mid size range of flows, it kind of was a reasonable kind of approximation. This is true across all the sites we considered. The prognostic model without brittle fracture, so this is in dark blue, does struggle to capture the shape of the distribution for these mid-sized flows. And kind of, this is part of the reason which we then included the brittle fracture, so model with brittle fractures in light blue, just because it's possibly not the whole solution, but we think this is a piece of missing physics that perhaps explains the discrepancy between the observations and the model. And the motivation of kind of this particular comparison is to make sure that both our version of the prognostic model and the power law model were kind of in reasonably comparable states to observations, so that we can run them both in simulations and kind of compare the different impacts. So this is what we've done. And firstly, we looked at kind of time series of the March extent and volume and September extent and volume, and we're comparing the models to kind of observations for the extent, so both Bootstrap and NASA team, and also high mass reanalysis. And actually what we find is that for both models, the impacts, there are impacts, but they're quite small on the Pan-Arctic kind of metrics, but they're quite small compared to the difference between the standalone simulations and the observations or the reanalysis. So like in terms of kind of this discrepancy, like they're not making a substantial difference. But then if we go to kind of the regional impacts, we do see larger impacts. So particularly in the MAZ, we can see quite large reductions with both models really, like in terms of CA extent or the CA area fraction and the CA thickness. But actually, this is where we can actually start to look at some of the differences between the models as well. So for example, we actually see quite a large reduction in area fraction with the prognostic model in March, and it's a bit hard to see, but it's substantially less for the power law model, whereas by September, the kind of the reductions in MAZ is comparable. And what's going on is so over winter, new flows form within the within this region in particular. You have lots of new small flows that form both from the kind of the freeze up in winter and also break up by waves. And these melt out in the early melt season, and generating these large lateral melt rates and quick reduction of sea ice cover in the early melt season. But by the late melt season, they melted out, and we see more comparable changes. For the power law model, because it has a fixed minimum flow size, you can't capture the effects of the melt out of particular flow sizes in this way. So we start to see these differences. And if we look at the effective flow size, then we can actually kind of visualize why we do see the differences in the models, because whereas for the power law model, it's almost like the effective flow size tracks the CS concentration, we see more variability kind of for the prognostic model, and actually see kind of lower values within the pack ice as well, and larger ranges of smaller flows within the MAZ, especially in the early melt season. So as said, we also had a look at kind of what might happen in the future Arctic. We took a simple approach to this. We just considered the evolution of the sea ice under future atmospheric forcing. So these simulations start in 2017 and run to 2060 using atmospheric forcing data. This is the RCP 8.5 pathway from HADGEM to ES in SEMA 5. And again, we look at impacts on the March extent and volume. And this is kind of a similar story. We are seeing changes in these metrics, but then it's not like a substantial impact on like the trends. So we're not seeing like inclusion of these processes isn't necessarily telling us that we're going to see an earlier ice-free Arctic, for example. Again, though, if we look kind of at the regional impacts, we start to see that actually, in a few, if we're interested in like the sea ice climatology in the 2050s, actually FSD processes are potentially going to be important there because for example, the prognostic model, it does have a pan-Arctic kind of impact on the thickness because, well, by that point, pretty much the Arctic is exclusively MIZ in this model. So yeah, so there's this story. Obviously, this kind of then raises this, this question of, well, if we're only seeing these kind of impacts, what sort of modeling approach should we take? Do we use a simplified approach, given we are worried about computational expense? Do we take the simplified approach of using a power law at a fixed shape, or do we want to use the prognostic model, which gives us a more higher physical fidelity in evolution? It's also worth noting that these are standalone simulations, so we can't necessarily assess the potential impact of ice ocean or ice atmosphere feedbacks. And I think that's kind of an important and open question. Okay, yeah, okay. So obviously, earlier I described the brittle fracture scheme, and I'm sure quite a few people are thinking that this is quite a substantial approximation of like two different processes that we're trying to represent here, the direct fracture and thermodynamic weakening. And obviously in practice, flows, like when they break apart, you're not necessarily just going to get flows in the smaller adjacent category. It could be a range of sizes that are produced. And also we're using a fixed restoring timescale. So we use a timescale of 30 days. We kind of calculate this based primarily on the thermodynamic weakening process. But in practice, kind of winter fracture events will happen quickly. The timescale for summer events will be much slower. And they will have dependencies on different processes. So like, obviously the melt pond area fraction is going to be important when it comes to this thermodynamic weakening process. But there are prospects for being able to develop and improve the representation of these processes in FSD models. So new observations, for example, from Mosaic, and also flow scale modeling from discrete element methods. And we've heard a bit about those today, and I think we're going to hear some more later, but I'm going to discuss those a bit here. Just to highlight further kind of the issues of the brittle fracture scheme. So we had this, as mentioned earlier, we had this brittle fracture constant. It's set to 30 days as standard. So we did sensitivity studies, one where we just took it out. So similar, well, we showed results from that before, and also one where we increased the impact of this brittle fracture scheme to 10 days. So at that point, it has a much stronger control over the shape of the FSD. And actually what we find is that without this scheme, we see an increase in volume of about 4%. So this is this blue line, dashed line, and of extent of around 2%. But by strengthening the impact of roller brittle fracture, we start to see reductions in volume of over 5% and in extent of nearly 8%. So actually compared to kind of our standard setup, this kind of substantial changes whether we even see a reduction from including the FSD model, or whether we actually see a more substantial impact from the prognostic model. So we do need to get a better constraint on these processes. So to do this, so SICE is a continuum model. I think we've heard a bit about this earlier today already, and we're not like able to resolve individual flows and the evolution of individual flows, which make kind of parameterizing any given process quite challenging. But what we can't use this as a tool to kind of motivate parameterizations. However, discrete element methods do model interactions between large number of particles. These particles can be free or bonded or round or polygonal, and they offer potential to be able to model processes at flow scale because we are able to resolve kind of the subfragment level of flows. So there's been several recent efforts to kind of develop DEMs for sea ice. So I think Hopkins et al. Was an early attempt in 2004, and there have been several models like occurring more recently. So I think we heard from Agnieszka earlier today about design. I think later we will hear about Sub-Zero from Georgi, and also SICU, which is a discrete element method that's been developed by Jenny Hutchins and Scott Dursky and others at Oregon State University. And this is some output. So I recently have been trying to do some work with SICU and still learning how to use it. So this is just an example of a kind of a toy scenario. I don't think the physics is optimized for sea ice yet in this setup. But this is just an example of how we can actually start to, so here we have kind of, we have a wind blowing in the north half of the domain, we have a wind blowing to the left, in the bottom half of wind blowing to the right. And we just kind of see how fractures form. So these red lines indicate like these fragments of ice breaking apart. And you can see here almost that you'll see this like interesting fragment size distribution forming. Okay, this last slide is just, so here I'm just wanted to highlight that to actually be able to model these processes, especially kind of the thermodynamic breakup of flows, we need thermodynamics in the discrete element method, which I don't think has been attempted yet. And actually there's quite a complicated set of processes. So this is just an example of some of the thermodynamics we see in SICE, also the next layer model, which is not relevant. But yeah, so this is just to highlight, actually there's quite a range of processes. So we need to represent sea ice melt in, we need a realistic representation of snow depth so we can get melt pond volumes accurately, and melt pond formation and temperature profiles, and also the relevant forcing as well that's not currently in the model. But we hope that to start to implement thermodynamic scheme into a CICM, so particularly SICU, and that is kind of my current work, to be able to kind of develop these parameterizations. Okay, so yeah, so there's been several recent efforts to improve the representation of flow size in sea ice models. We find this high sensitivity in the sea ice mass balance, both to varying FEC model parameters within the observed range, and also in the representation of model physics. So that sensitivity to the kind of representation of wave attenuation. Neither of the FEC models we saw produced a large impact on the Pan-Arctic scale, but over more regional scales, we saw larger impacts and potentially important differences as well between the models. We've used observations to kind of motivate the inclusion of a brittle fracture scheme into the prognostic model, but this scheme does involve several approximations, and we'd like to constrain it further and provide a more physical parameterization of these processes by using observations and flow scale modeling. Okay, thank you.
Any questions? Oh, I'm sure.
Thanks, Adam. I just wanted to clarify, especially for the future CI simulations, where you're getting the waves from, because I've always thought of this as playing, like potentially being important in terms of a feedback, as if you have increasing wave heights in the Arctic and then more breakup of sea ice, allowing more sea ice wave penetration and wave generation. And so if you don't have an interaction between the waves, I wouldn't expect to see very much of an impact. And then also with the having a reanalysis atmosphere, then you're also limiting the sea ice albedo feedback. So yeah, just wanted a bit more information on the wave treatment.
Okay, yeah, so with the waves, we actually, we did have some wave projection data, I think from a coupled simulation that we ended up not using with the model, because what we found with that particular simulation that when we looked at climatology from 2012 to 2016, well, the forcing data that we had versus climatology in the 2050s, we actually didn't find substantial differences. So, I mean, this was one particular setup, and that is something to bear in mind. Like, there are feedbacks, and in particular, if kind of the simulation that was being run didn't have an accurate representation of sea ice, then changing effects, for example, will also impact the wave climatology. So I think that's an important point, and definitely something to consider. I mean, in particular, the fact that we expect most of the Arctic to be atomized by 2050s, potentially shows waves will have a much stronger control. And I think that's, yeah, an open question, I think.
Any other questions? I'm just a little curious about, I'm just a little curious about the marginal ice zone is often defined in terms, well, it can be defined in terms of waves and so on, but it's also defined in terms of, say, 15% to 80%. And I'm kind of curious, in other words, the waves coming for the sea ice concentration field. How about for waves coming in? How about those outer fringes? You know, in other words, that's really, in some sense, that interface between the open ocean and the quote marginal ice zone. And so I'm curious if you've looked at what's going on in these fringes and if that affects any of these kinds of issues.
Yeah, I mean, the setup we have is not going to be great for, like, in terms of like specific wave interaction. Yeah. Won't be great in terms of like actually, like if we're interested, for example, in how kind of that interaction changes for wave propagation, we use a very simplified wave treatment, so I don't think this kind of framework is a good setup. But I think we do tend to see that actually, like those kind of outer MZ regions, we tend to see very large increases in melt rate. So these are often the kind of places, as you might expect, these places you do see the largest impact of kind of the wave component. So quite often we see these big changes in the Greenland Sea, especially kind of in the early melt season, because that's a region that is kind of exposed most often to waves and wave breakup. So I guess it is an important question of how the models are representing those interactions, because I guess it's a question of how, you do expect, I guess, flows to be quite small in this range just because of that constant exposure. But yeah, it's probably not the best framework to be able to explore that question.
Great. All right, well, let's thank our speaker. And then